for my TAs by not filling out the attendance form the way that it instructs. So it actually does cause a problem for them porting the data over into the attendance sheet if you don't follow the instructions. So please use your ASU your ASU email, not like your personal Gmail or something like that, and your full name, not just a partial name. Doing those two things really will make a difference for them in collecting your attendance. And I don't know if you've ever heard the saying, a happy wife is a happy life. Well, a happy TA is a happy, yeah. You always want to do things that get you on the good side of the people that have an effect on your grade. So it's a small thing, really. But please, full name, ASU email. Fair enough? Okay. Well, all right. So, sorry, just collecting my thoughts for a second. All right. There was, so we've got everybody in groups now. There was one group of 3 people that were left over. I didn't want to do 3 groups of 1 or anything. So I sent out a note on Piazza to those 3 people. Please communicate and yeah. I don't know about the other ones because so if you didn't put yourself into a group and you didn't just receive a notification on Piazza, you need to reach out to the TAs because they have your group information. That's the solution we're going with. Okay. Okay. Any questions about groups? Great. So not much of a review from last time to give because last time we talked about the group project for the semester and did a little intro to Python. Hopefully that was instructive. Hopefully that was interesting, at least to some level. I know a lot of you have some familiarity with Python, but at least that last part where we talked about how to take a binary file and extract fields from it, hopefully that was helpful for the homework. So the only review question I have for today is, what is the programming language requirement for all homework assignments in this class? Whoa! Come on, this is not elementary school. Yeah. Yes, it needs to compile in Ubuntu. All right. So actually have staged some changes for the website that I will be posting today, along with the link to the recording and slides and stuff, that has like the general instructions for submitting homework with a little bit more detail and links to introduction to make files and thing like that. Okay, so that'll be hopefully helpful to you as you develop that. So those of you that came in a little bit late, I've just got to reiterate this one more time. So the TAs really need you to use your ASU email and your full name when you fill out the attendance form. It makes a really big difference for them. Okay, let's go ahead and jump in. Switch over to this. Okay, so today what we're going to talk about is evidence acquisition. So this topic is the last topic that falls on the side of processes of forensic stuff, okay? So that means that after this topic, that's when we can start taking a dive into technical areas and really starting to explore them. So, for example, we're going to start off with disks, volumes, and files, like what they are. Because, yeah, you've worked with them, but have you really dug into the details of what they mean? So that's something to look forward to after today. At least I think we'll be able to cover this whole topic today. But are there any outstanding questions in your mind about the forensic process, rules of evidence, any of that? That you just have like this burning question, but you weren't courageous enough to post it on the No? Okay. All right, we'll go ahead and get into it then. So acquisition. Acquisition, what is acquisition? Someone give me your definition of acquisition. Talked about it before, right? Where have we seen the term acquisition before? Let's start with that, yeah.
The process thing.
The process thing, yeah. I guarantee you if you put that down as an answer on an exam, we will struggle to give you any points. Yeah, so come on, give me a better answer than that. Where have we seen the term acquisition before? Yeah.
I was just gonna say, like, collecting evidence using the process so it's admissible.
Yeah, yes. It's the first step in the forensic process. Yes, that's where we've seen it before. So you talked about how it's what we do in the acquisition is we copy the evidence or the data without altering or damaging the original data or the scene where it was discovered. That might seem a little bit weird to tack on that extra little bit there, but if you think about systems that are a little more delicate or have been booby trapped for some kind of logic bomb, if you unplug stuff, that's what we're talking about, right? Don't disturb the system while you're making a copy of it because it might compromise the integrity of it, right? So here's a question. Can you think of a circumstance where analyzing the original version of the data would be impossible? Let's say, so what I'm saying here is if you couldn't make a copy of the original, analyzing the evidence wouldn't really be possible because you have to make a copy before you can analyze it. Tricky question? Or just late in the afternoon? Yeah.
Would that be like when you're analyzing like network packets and the packets aren't actually there anymore, but you're going through logs to kind of extrapolate what was sent?
That's a really good example. Yeah, so network traffic, you're not going to analyze the original packet, right? You're going to either analyze a packet capture or a log. Probably not a packet capture unless you like have a very targeted subject that you're trying to analyze or to gather information on, and you have like a time frame that you look at, and it would be really difficult. Or logs, yes, so very good. Let's think of another one. Any kind of digital information where analyzing the original is not possible. A streaming service. Give me an example.
So perhaps there's a service similar to Netflix, but they only offer like illegal content, like let's say porn, and you have to connect to it, and they'll stream it. So you don't actually, or whoever is connecting to it doesn't have the actual contraband. It's on a server somewhere where the police don't access it, and it's being sent to the person who's still viewing it.
Yeah, that's I like that example where the content is streaming. The content itself is illegal, but you can't actually capture the stream. Yeah, very good. Okay, come on. There are a couple others that I can think of. Of course, I've been thinking about this for 10 years, but you have that advantage. What else? What is there, but when you try to touch it, it's not there? Thoughts?
Yeah, I was gonna say, this isn't right, but I was gonna say like file metadata, like if you are on the system itself and you're modifying or accessing files, that you would adjust the file metadata associated with them. So you want to make a copy.
Yeah, so that's not an example, just like you said, because that data we assume is going to rest on whatever storage device, right? So there's a file system there that we know how to interact with, all that, right? So that's not an example. Yeah.
Probably doesn't apply, but maybe like somebody took a picture of someone else's computer and you don't have that actual computer, but maybe you're trying to figure out the files. You don't have the files metadata, but you have the pictures metadata.
Yeah, that would be really hard to use as evidence, right? To say, well, but I took this picture of it. Yeah, that would be tricky. I don't know how you convince the judge of that. Yeah.
With like cloud files,
Yes. Why?
because they're
Can you
not,
get the actual file?
no, they're just distributed.
No. When you download a file from Dropbox or Google Drive or any of the other services, the company is giving you a copy of the file, right? The original file is on their servers. They give you what they want to give you, right? And who knows what's going on in the middle, right? Yeah, very good. What else? You think of anything else? Yeah.
Would environment variables that are on the system be something that would fall in this group?
You're on the right track. Environment variables, what do you do forensics on environment variables? That's definitely metadata for a system. I don't know, I mean, if you're going in the direction of like malware forensics, I can see how that would be important. But you're on the right track. You're on the right track. Think a little more general. The environment variable is really specific, right? Yeah.
If the original data was improperly handled during the acquisition.
Oh, yeah, absolutely. Yeah, if it was improperly handled, yeah, it could be damaged, and then you wouldn't be able to analyze it or make a copy of it. Yeah.
I'm going to try and generalize it and just say environment.
Environment.
The environment that the target software file, whatever you're trying to analyze is, like when he says environment variables, those are not persistent. So even if you copied your drive and made a copy of it, you can't get it. So you can't capture it without analyzing. Well, I guess I'm analyzing the original, so I'm answering a different question.
Well, where is the environment? Where is it stored? RAM. Can you analyze the original version of RAM? Why? How would you do that? Right? Think about it. So RAM is what the CPU is using to do all this processing, right? You turn off the power, all that data goes away. So in order to analyze the original, there's kind of two options. You can either do a cold boot attack when you like freeze the RAM, put it in another thing, right? But then that's tricky. So if you're going to leave it in the system where it's installed, you have to occupy the space of RAM, right, to actually do analysis on the RAM. You see what I'm getting at?
You gotta use the RAM to look at the RAM unless you
Right.
freeze it.
But like, how are you going to make a copy of your RAM? Are you going to fill up RAM with? You see where it's kind of like cyclical. So you can make a copy of RAM elsewhere, and there are programs that do that. And that's how you do RAM. That's how you do memory correctness. And in that case, you cannot analyze the original because you gotta make a copy if you're gonna like dig into. Because in RAM, one of the things that is in RAM is the file system structure, right? That's how you find files. Is your whole file system structure gets imported into RAM. Even that, like, I lost my train of thought. Dang it, I hate when that happens. Anyway, it's not possible to analyze the original version of RAM. So hopefully that was an interesting-ish thought experiment. I got your juices flowing a little bit. Okay, so back to acquisition. So acquisition, we have to do acquisition concurrently with authentication. The reason why is, well, we've got to prove that the recovered evidence and data is the same as the original data. Like that's the purpose of authentication. But why do we have to do the authentication concurrently with the acquisition? Why can't we do it later?
Well, I mean, how are you gonna prove, like, after the fact, that the copy that you made even is like the original evidence?
Well, we'll talk about some techniques for that today, but I think you're not quite hitting them. Here, let's keep thinking about it. Yeah.
Because like, let's say that if you do them like one first, then the second, and your authentication fails, and you have to go back to acquisition, it's possible that
Yes, and who might have been the one that changed it? Us, during the acquisition process, right? That's the key, is that we don't want to be the ones responsible for the actual compromise of the evidence, the original evidence, right? So that's why we've got to do it concurrently. Okay, so purpose of acquisition. Why are we making a copy? I want you to imagine this scenario. So while examining some files on a hard drive, the examiner forgets to turn on the write blocker and some file attributes change. The examiner argues that none of the files impacting the case were affected, but the consequences of this kind of scenario are, well, the defense might claim that the evidence is no longer trustworthy and should not be admitted. Remember, that's one of the 4 rules of evidence, is it has to be admittable. Man, I thought I got good sleep last night, but I guess not. And perhaps some important files were changed, but the examiner has no way to know for sure because they didn't do their job well. So this is similar to some of the other stories I've told you about guys playing games on a computer that was brought in and stuff like that, right? So forensic examiners can't risk compromising the evidence or changing it without meaning to. It could mean the difference between proving someone's innocence or guilt, and that's really what we're driving at here. So, and that's why we always work on a copy instead of the original evidence. Okay. Okay, a little bit more on the purpose of we were talking about the purpose of acquisition, so let's talk about the purpose of authentication real quick. So the acquired copy of evidence provides protection for the original. We've kind of gone over that already. The authentication proves the copy is exactly the same as the original, and today we're going to talk about some techniques for actually doing that proof. How can you prove that two digital things are exactly the same? Well, there's a couple approaches. You could look at every single bit. Does that sound tedious or what, right? Or you could compute what's called a cryptographic hash of both the original and the copy. Who here is familiar with a cryptographic hash? I'm hoping that most of you would, because I believe that that's part of the required content for 365, right? Do they talk about hashes in 365?
Yes.
Yeah, I know some of you are taking it concurrently with this. So anyway, okay. So we're going to talk about hashes, otherwise known as cryptographic hashes, hash functions, message digests, all the same. I'm going to use them interchangeably. Okay. All right. So message digests, also called cryptographic hash functions. The purpose of a message digest is to uniquely identify data using the data itself as the source. So rather than saying, so what I mean by that is in a file system, you have some kind of index of the files, right? And you identify a file by some name that you give it, or a location on the actual, within the file system itself, right? That's how you identify it. But here, we're identifying it with something that's generated from the file itself, rather than putting an external label on it. If you move that around, you can still do the same thing because you have the method by which that label was generated. Does that make sense? Or did I kind of talk in a circle? Okay, cool. Exactly. So, just like I just said, it is better than index because other people can generate the same identifier just using the data. Okay, so one requirement that we have is it should be easy to generate for any of the inputs, so the message or the file, whatever it is. Another purpose of hashes is that it should be infeasible to find data that will generate a specific digest, meaning you shouldn't be able to process it in reverse. Another requirement is it's infeasible to find two messages that will generate the same digest, and the digest changes if the data changes. Digests are usually based on lossy computations, meaning that you're losing input. And we'll talk about each one of these a little bit more in depth as we go along. And just as a final note, requirement 3, being able to find two messages that will generate the same digest, it's called a collision. So if I use that term, that's what it means. Okay, so pictures help sometimes. Let's say you've got some original message file. Doesn't matter what size it is. It can be of infinite size. What a message digest does is it takes that, and using some algorithm, it has a digest output that is smaller and is of a fixed size. Now, going this direction is relatively easy. Going this direction is very hard. And that's like the super high level view. Let's talk some actual specifics. So let's say you've got some 20-letter password that you enter into a site. What they should be doing, in addition to salting and all that great stuff, is computing some digest and storing the 128-bit digest, okay? Not the plain text password. That's how it should work. But what's great about hash functions is that if you have a 20 megabyte PDF file, use the same hash function on it, what will you get? A 128-bit digest. Doesn't matter the size, 20 letters, 20 megabytes, or a 1 terabyte hard disk. Same thing, 128-bit hard digest. So that's very convenient to be able to identify uniquely a lot of things without the size changing based on the input. Okay, that's what I'm kind of getting at with this slide. So we talked about how a hash function should be one directional, right? It should go in one direction. Going the other direction should not be easy, should be computationally infeasible. So infinite input space. Hash function, relatively small output space. So it should be impossible to calculate M, which is the message, the input, from the hash of the message or the output. I feel like I'm talking in circles. I apologize, but hopefully reiterating this a few times will help it sink in if this is new to you. Okay, so what I mean by that is if you have the 128-bit digest and you know the algorithm that created it, there's no like magic reverse algorithm to get the original. And that's because we lost a bunch of data when we went through the algorithm, what we call a lossy algorithm. So there's no way to come back. Collisions. So because we have a lot of input and relatively small output, there's this principle called the pigeonhole principle, which states that if you have n items, hopefully discrete math taught you this. If there are n items put into m containers with n greater than m, at least one container is going to have more than one item, right? That's a pretty logical thing. So you've got this infinite input space and finite output space. Of course, there are going to be duplications in the output, right? But the thing is that if you have a really good hash function, that should happen very rarely. And there are a couple of algorithms that have been, I'm talking about that next. Yes, it is. There are a couple of algorithms that have been used that's no longer the case. So MD5, Message Digest Algorithm 5, yes, there was an MD4 and an MD3. So it computes a 128-bit digest. It's one of its advantages is really simple and compact and fast. But when people created this algorithm, they thought it had a 2 to the 64 collision space. Ends up it's just 2 to the 20.96. That's a huge difference, right? in collision space. So not nearly as strong as they thought it was when they created it. SHA-1, it's actually quite similar to MD5, creates a 160-bit digest instead of a 128. But the thing is that both MD5 and SHA-1 algorithms are now considered broken. So if you use Git, still uses SHA-1 hashes. That's the thing, though, is that those aren't meant to be cryptographically like it does. We're just identifying stuff. We're not like trying to hide a secret, right? Because the content of a commit is public, so that's why there's not as much of a concern with Git and commits. But pretty much, you shouldn't use MD5 or SHA-1 if you care about keeping something a secret. Okay, so there's some SHA-2 family hashes just for your information. 256, SHA-512, each have respectively 256 and 512 bits. Currently, as of when I researched this, there's only theoretical attacks. But then there's this whole new family of SHA-3 algorithms. And the purpose of SHA-3 wasn't to replace the SHA-2 family, but to just have a completely different algorithm. Because as I understand it, I might be wrong because I'm not a cryptographer, but as I understand it, the SHA-2 family was kind of built upon the algorithms of the SHA-1 family algorithms. So to kind of completely have, avoid any attack vectors that would be common to all those families and the direction they took those algorithms, they just started over completely. And that's what they did with the SHA-3 family. So a much higher, much bigger digest than what we've seen before. So the last one, 512, SHA-512, you can see that going up from 512 to 1600, it's a lot bigger digest. Yeah, what's up?
Does the more bit digest means more secure or messenger?
No, it doesn't. Not inherently, not by itself. So to kind of think of it a different way, let's say I created a hash algorithm that what it did was basically just save the last 1600 bits of the input. That's it. Is that secure? Or would it be really easy to reproduce a lot of input that would have the same output? Right, so it all depends on the algorithm. Now, having a similar algorithm but much larger bit space means that the output space is much bigger. So even just that property alone means that you should have fewer collisions and thereby higher security. Do you see the distinction there? So one property of a hash function isn't enough to increase really high. You've got to have a balance between properties. Good? Any other questions? Yeah?
Is there a procedure for get lucky, you have to say, I want
So the question is, if you happen to be really unlucky and catalog two pieces of evidence that have the same hash, is there a procedure for handling that? Basically, so a lot of forensic tools have been pretty much hard-coded to use MD5. And when MD5 started to look like it was not very secure anymore, what did they start doing? Well, let's just take the MD5 and the SHA-1 hash of everything. And that seems to be still a pretty common occurrence that you have MD5 and SHA-1 for the same file. And that's how you kind of avoid collisions is you use two different algorithms. There are, of course, problems with that, but that's kind of been like the shortcut to having that problem. Answer your question? Yeah. Yeah.
I'm just curious, like, how did they figure out, like, the first section, third bullet point, like, the vision? Like, how did, like, it just seems like a huge thing.
Do you know how Unix was created? So they found these really amazing machines that took as input beer and pizza and output really amazing code. I kind of say that in tongue in cheek, but really they're people that just come up with really great ideas, and you just have to fuel them with beer and pizza, and they just output really awesome stuff. Cryptographers, that's an area of computer science and mathematics that I don't, that's dark. I don't even, my brain does not function well when I try to think about it too hard. So I don't know. I don't even know. But I'm sure there are really great conference papers that would explain it in detail that would put you to sleep like that. Yeah, what's up?
When you talk about how forensics tools use MD5 and SHA-1, do they run the output of MD5 through SHA-1 or keep two separate indexes concurrently?
Okay, so are you asking if both indexes concurrently? Yes, so they compute, they put the file through one and then they put the file through the other and they store both values. Does that answer your question? Yes. Okay. Yeah, it wouldn't make much sense to take an MD5 hash and just take the SHA-1 hash of it. If there's already collision at the MD5 level, it's going to be the same.
If we shouldn't use SHA-1 for anything important, why is that what we're using in our project? Is our project not important?
Because it still remains an industry standard for things like blockchain, Git, and I mean, I very well could have put a bunch of hash algorithms on a dartboard, and I just wanted to make it standard. So, no particular reason. Very insightful question. I'm glad that you read the project description. That shows me you're taking initiative. That's awesome. Okay, any other questions about hash algorithms? Okay, I want to stop talking for a minute, so we'll take a 2-minute break. No.
I don't know if you want to.
No, let's go ahead. Yeah.
Why don't you post this slide?
In case I have to make changes. And to encourage you to come to class.
It would just be nice to like.
I understand.
What if on the Google survey link there's a count?
Because topics, so the slides are arranged by topic, not by lecture day, right? So we took 2.5 days to cover topic 1, right?
That was a good idea. It made sense.
I like the idea of your idea, but not the idea.
I'll just go back and fill out my list.
You'll do what?
I'll go back. I'll just go back.
Okay.
Camera wasn't working at the beginning of class. Would I be able to get at the end of class or now see that? Oh, and it's not working again. Hold on.
I started when I was running out. Yeah.
Okay, let's dive back in. But before we do, have any of you noticed that I actually live stream these recordings? No? Yeah. So it's on YouTube right now. So you can totally tune in. Don't do it right. Don't. Could have stopped you, but it seems like a lot of wasted network, man. Anyway, so you ever like homesick or whatever, and you're just like, oh, I need some forensics. Oh, Mike's lecturing right now. I'm gonna tune in. Totally can't. Just don't take it. Oh, don't do the attendance. Don't you do it.
I thought you was that you did attendance before you started.
I know, but it just. Could you
print it off and like hang it up?
I could, but then I would kill a tree every day. Okay, let's talk a little bit more formally about the desirable characteristics of a hash. Okay, first, performance. It should be easy to compute H of M. Now, that doesn't necessarily mean that it will go fast, because that's a different, that's something completely different, right? But it should be easy. Trying to think of a counterexample, nothing's really coming to mind, but it should be easy. Pre-image resistant. That's a fancy way of saying that it should be computationally infeasible to find an N that you meaning find an N that the hash of N is equal to H. So if you already have a hash, you should not be able to say, oh, I can totally match that hash with this input. Okay. Second pre-image or weak collision resistant means that given a message M, it's computationally infeasible to find a different message M prime such that the hash of both messages is the same without the messages themselves being the same. It's a birthday attack, right? So for those of you that have studied cryptography at all, who can tell me what the birthday attack is? It's kind of fun. Nobody? Adam can. He's glaring at me. Okay, so the idea is with the birthday attack is that if you had to guess, actually, if you had to guess, how many people do you need to have in a room before at least two of them have the same birthday? 23, yeah, it's like 23 or 50, something like that. It's a lot lower than half of the number of days in the year, because it just works that way, right? When you got, I don't know, that's the, don't laugh at me, that's the cryptographic technical term for
every day you add, it reduces the search space for
yes.
the rest of the day.
Oh, there we go. See, I knew I had a TA for a reason. No, I'm just kidding. For every day that you add, you remove a day from the search space that you're looking for. That makes sense? So I have a birthday on this day. Okay. Now another birthday on this day. Okay. Now you're increasing the search space of what you're trying to find a match for. Right. And since there's only 360 6 possible days that you could have a birthday on. Well, I have a brother-in-law that's born on February 29th, but they're a separate case, right? They throw off our easy computation. Okay, second pre-image, birthday attack. 2 messages that are different, have the same hash, should be hard to do. Strong collision resistant means it's computationally infeasible to find 2 messages, 1 and 2, such that the hash of 1 and the hash of 2 is the same. Oh, yes. So the difference between the previous one is that you already have, so you have a message that you're trying to, okay. So the strong collision resistant, wait a minute, hold on. Am I getting confused here? Of course I am. Strong collision resistant, that's the birthday attack, right? Someone said that with confidence, right? Okay. This, you're trying to find any 2 messages that match. This one, you have a message, you have an input, and you're trying to find another input that collides with that one's hash. That's what the math notation is telling me. Am I reading that correct? Okay.
You change the message, tweak it. Still keep the same.
Yes, yes. So that was one of the first proven, like, real world, not theoretical attacks against MD5 algorithm. Was they had this document and a similar, like, Word document that only a little bit had been changed, but the hashes of the 2 of them were the same, and that's second pre-image or weak collision resistant. Okay. Enough tech talk, right? Let's talk about acquisition types and methods. So there's different ways to go about the acquisition process, and that's what we're going to describe here. So first of all, we've got live acquisitions. What's a live acquisition? Yeah.
Packet capture.
Oh, that's an example of one. Yeah. What's the definition though? Can you give me a definition?
Acquiring the data as it is created.
Yeah, so the system's still running, basically. So network forensics is kind of its own thing. Trying to think if I've ever heard of live and static used to refer to network forensics. I don't know that I have. So you got to think more like computer systems, right? So live acquisition of a computer system is the system is still running, meaning the data is still available in RAM. And that's the crucial part, right? Because a lot of times, if the system is encrypted, taking a live acquisition is the only way to recover the decryption keys so that you can actually analyze the data once you've taken a copy of it. And so the thing, though, about live acquisition is that you're inherently trusting the system to give you the data that you're asking for. And what I mean by that is you've got this computer. You're trying to do an acquisition on it so that you can analyze the data later. What you do is basically start using the computer, right? Now, we've been talking about how it's very important to not alter the state of the system you're trying to acquire, right? So there's kind of like this little provision here that if you happen to know or suspect that the data is encrypted, there would be reason for taking a different route for acquisition. Okay. And in that case, if you have to violate the integrity of the evidence, that's the only way. You have to be able to back up that argument and then give the reasons by giving the reasons for it. Yeah. Question?
Yeah, but you said if there's reason to believe something is encrypted, But nowadays, I mean, Windows does its BitLocker, Mac does their thing. By default, most consumer personal computers, it is reasonable to assume they have some sort of encryption.
Right, but from an academic standpoint, where we are, right, we present the ideal scenario of you don't mess up the system at all. And then we say, okay, well, in the real world, we have a lot of encryption. And so live acquisition becomes a necessity. There has to be a provision for it. There has to be an accepted way to change the system state. And that's what we're talking about here. Is that fair enough? You still don't seem satisfied.
We're good.
Okay, yeah.
Is there any way to like flush out whatever you have in your RAM, or I guess a better way to word it, how long is that information stored in your RAM? Or does it
I think I know which paper you're going to choose to pick to review. Yeah. So stay tuned, because I think so. I referenced it earlier, but one of the papers that you'll be able to select for your paper review for the semester, it's called "Lest We Remember," and it's describing what's called cold boot attacks, where you literally take a can of computer cleaner spray, which is just liquid nitrogen, right? Turn it upside down so that it sprays the liquid nitrogen out. You freeze the RAM because there's a direct correlation between the temperature of RAM and how quickly it dissipates all of the electrons that it's storing in it. Pull out the RAM before it loses all that memory, put it into another system, and grab everything from it. Okay. Yes, it is. And there's a cool video that goes along with it. So stay tuned for more information about cold boot attacks, because we'll talk about that. Okay. Actually, you'll talk about that. I'm not going to talk about that. I'm excited. I'm so excited for the paper presentation. I didn't say that. Okay. Okay. So inherently trust the system to get the data. So the textbook relates this to walking into a crime scene where there's a dead body on the floor and there's people in the house when the police come, right? And the policeman says to one of the people that was there with the dead body, "Hey, will you go get this thing for me from the other room?" And they go out of your sight into the other room, and they either say, "Oh yeah, I wasn't there," or whatever. That's what it's like to do a live acquisition, because you're using the system's operating system, their file system, their everything, right? Processes are running on that system that might be subverting your view on the file system. It might be sorry, that was a really fancy way of saying it might be hiding files from you. It might be hiding data from you intentionally. How do we know that? We don't, because the system's running. It was in the suspect's possession. It could be in whatever state. We don't have any guarantees. So there's some trade-offs to live acquisition. Now, the second form is static acquisitions, sometimes referred to as dead acquisitions, because the system is no longer running. It's turned off completely. This is the preferred method for all the reasons that we just talked about, right? The data is at rest. It's not in RAM. It's not running. There's no processes hitting it over and over again. It's completely static. Static is a great word for it. But it limits the data that's available. You don't have any of the information about running processes or decryption keys or any of that, because that was in volatile memory that is now gone. You don't have access to it. It's just floated off into the ether, right? No RAM data, no way to decrypt, okay? All right, so what are the two acquisition methods? Yes, the answers are on the board, but I want you to internalize it. What are the two acquisition methods?
Live and static.
Live and static acquisitions, okay? Don't forget that. That's kind of a big divide between, so we did this really cool research project. It's one of the papers that you'll be able to select on email acquisitions. And we argued that our method was valid because if you compared it to live acquisitions, there was a need for it. Just like in certain email acquisitions, there was a need to still get data even if the system wasn't static. And so knowing these two is important. Okay, 3 acquisition methods. So these are ordered from the least amount of data collected to the most. The first one is called a logical acquisition. Anybody want to guess what a logical acquisition is? What do you think? What does it sound like? Bits. I mean, you do get bits from it, but it would be hard not to, right? What does it sound like? Logical acquisition. Yeah.
It's sort of like, I'm just thinking about like file systems, like how you have a logical disk as opposed to like multiple different, like the actual implementation might be like multiple disks in RAID, but then you might have like a logical disk that represents all of them in constant.
Okay, so translate that, superimpose that on acquisition. I'm doing this more to like get you to be like, oh, what? Because it'll mean more to you when I give you the right answer, right? If you thought through like 5 wrong answers, right? This is a teaching. I'm not just lazy, a little bit, but yeah.
Maybe logical isn't like targeted. You know what you're looking for example.
Yeah, very good. So you're capturing specific files. You're looking for specific. Or this could be file types too. So you maybe you don't know the exact file name that you're looking for, but you know the type. So you know that. I mean, a really classic example is child pornography, right? Any image files are what you're interested in. You don't really care about their Excel spreadsheets, right? For that kind of a case. It goes back to knowing the purpose of your investigation, like we were talking about when I introduced the processes of forensics. Yeah, very good. So another great example, if you're doing an email investigation, PST and OST files, what are those? Yes. Outlook, yes. So personal storage table, I think is what PST stands for. And basically, it's a local cache of your emails in Outlook. So if you use Microsoft Outlook. Okay, so the focus of a logical acquisition is at the file system level, meaning it relies on the file system to list the files correctly. And that'll become more clear in the next topic, what I mean by file system level of focus. Sparse acquisition is the second one. What do you think this one is? This one's a little trickier. It's not as easy to kind of deduce as logical acquisition. Yeah.
Maybe it's like you're getting like the raw data that's on the machine, but not all of it.
Actually, you're right. So it's everything that logical does, but it also includes fragments of unallocated or deleted data. That's what a sparse acquisition is all about. So the focus here is at the partition or the volume level. So see, the one of the problems with this course, with teaching this course, is that you've got this subject, and this subject, that in order to really understand all 3 of them, you need to understand the other 2. All right, so it's hard to like jump in and be like, okay, I'm gonna explain all 3 of these to you because you kind of have to take them one at a time, right? But then you come full picture and suddenly you understand the first one a lot better because you understand the other 2. Does that make sense? So that's what's happening here is I'm telling you the focus is at the partition or volume level, but you don't really know what that means. So what I'm saying is you got to come back and study these slides after we talk about the next topic. Fair enough? So if you're confused, just come back later. Okay, last one is bitstream copy or bitstream acquisition. Same thing. Okay, so what is this? What do you think this is? What does that mean? Yeah.
Reading the bits off the physical media itself.
Yeah, exactly. So it's an exact bit for bit copy of the entire device. We also refer to this as a forensic copy. So when you've got a hard disk that has been unplugged and you take a copy of it, this is what you do. You do a bitstream copy of it. And it's static and you just go right ahead. Okay, so this includes all the files, fragments, and et cetera. So, but the focus is at the disk or the storage medium level. So on your disk, you have volumes, and inside volumes, you have file systems. And so that's why there's different layers of focus for these different acquisition methods. Okay, so one little note, a logical or sparse acquisition may be more appropriate in the following circumstances. If the time is limited, or if the original storage isn't accessible, such as in web or cloud forensics cases. Okay, a little bit more on bitstream acquisitions. There's two types of bitstream copies, bitstream disk to disk. So, yeah, what's up?
In the sparse acquisition, how do you decide what spaces of unallocated memory to take? Or are you just shooting in the dark?
Okay, so to know what spaces in the file system are unallocated, you have to understand the file system.
But are you taking all of the unallocated space?
Yes, you are. So think of it as, rather than looking through the file system for specific files, which is what logical acquisition does, you are taking, you're lifting the whole file system and saying, I'm going to analyze this. But it's different than saying, I'm going to take this whole disk and analyze this, right? Because, nice. Sorry, that's okay. Because you have more than one file system in a disk, right? So by taking a whole disk, you might get more files. Yeah.
So kind of as like an analogy to this, like if your disk was like a filing cabinet, with logical acquisition kind of be like you looking for a specific folder maybe. And then sparse acquisitions, like you take a drawer of a bunch of different folders, some of which might be empty because they're like deleted.
Yeah.
And then bitstream is like you just take the whole cabinet.
Yes. The drawers, the hinges, the casters, everything, the whole thing.
So is that an appropriate analogy?
Yeah, it's great nowadays. Okay. Bitstream disk to disk. So when you take a copy of this disk, you stream all the bits and put them on another disk. Okay. So what this means is, contents of evidence written to storage device that exactly matches the make and model of the original, a literal duplicate of the original. So you've got a Hitachi hard drive model, blah, 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 and that's the original that you collected at this crime scene. If you're going to do a bitstream disk to disk, you've got to find that exact model with the exact same volume, everything. And now, why would you do that? There must be, the only reason you would really do this is if there's something about the actual storage device itself that's important. I'll leave that to your imagination as to what that might be, because who knows, right? But there are cases where that's been the case. And, well, I don't want to go into it. Okay, so has any of you ever used one of these? Yeah. Other than just to save something, right? It's not just the save icon. That's a floppy disk. Okay. So this is the illustration that the current version of the textbook still uses a floppy disk, but whatever bits are right here, you take them from the original and you map them to the exact same spot on the other disk. Okay, that's what this is illustrating. Okay. Second type of bitstream acquisition is a bitstream disk to image file. So in this, instead of taking all the bits from the original disk and moving them to another disk, you're creating a virtual disk. Now, the output of that is basically just another file in your file system, and that makes it really portable, right? and because of that, it's more common. It's referred to as an image or an image file. The file is the exact size of the original evidence, which means wherever you're going to store it, it needs to have enough space to store the image of the original, right? You copy to something bigger because you got a file system and everything on this other one that has to account for everything from the original. Okay. So the original disk, instead of going to another disk, just goes to some file. There are all the bits. Anybody comes back with the message that's in that file? No, don't waste your time. Okay. Okay.
Actually, a message?
I don't know, man. Okay. Any questions about bitstream acquisitions? Yeah.
So what would the case be if like you were rating like a server or something and there's like a lot of data? Do you just like have to get a lot of storage space to like store all of that when you put them in files?
Let's talk about the next topic, evidence formats. So what you're talking about is happens to be the first type of evidence formats that we're going to talk about. Raw, okay? So raw image formats are just a bitstream image file, right? You got all those bits from the original evidence, and you just take them and blast them out to an image. So the advantage of that is that it's really fast in terms of like taking it, but it's uncompressed. So for data transfers from this disk to that disk, there's no processing in between that has to happen. So you can just write it right out, but it's uncompressed. So this can ignore minor data read errors on the source drive. And this is called the universal file format because everything else, well, a lot of the other formats we're going to talk about are designed for a specific tool, right? So this doesn't have any kind of tool that it's associated with because it's just like the original disk. There's no formatting to it that's been done. Some of the disadvantages, excuse me, that it requires just as much storage as the original disk or data, and tools might not collect marginal or bad sectors. Why would you care about bad sectors? What is a bad sector? Yeah.
It's like physically damaged, otherwise like unreadable.
Yeah, unreadable. Sometimes a bad sector is still readable, but not writable, right? So it might have data still in that sector. If you don't know what a sector is, there's another one of those things that's codependent, right? We'll talk about in depth next topic about what sectors are. But there might be data still there that if you could read it, it would give you information that might be insightful, have passwords or who knows what, right? Okay. Proprietary formats. So, oops, sorry. Some features of proprietary formats is it's compressed. So this is where we address the question you just had about if you had to acquire a big old server with 20 terabytes of storage, well, is there actually 20 terabytes of data on there, or does it just have a 20 terabyte RAID array, right? Different questions. So another thing that you can do with proprietary formats is split it into smaller segments. So if you have a gigantic image, you don't necessarily have to have the storage capacity for the whole thing all in one go, okay? Also, another really great thing about some of these proprietary formats is you can integrate metadata into the image file, meaning metadata about the files or what you discover there that wasn't part of the original disk, the original data, but that you add to the forensic file for purposes of like indexing and things like that, okay? Some disadvantages, inability to share images between different tools. That's gotten a lot better in the last several years than it used to be. File size limitation for each segmented volume. The unofficial standard for proprietary formats is the expert witness file format. You can identify them because they end in E01, E02, etc. Okay, advanced file format. I'm gonna make it, right? I'm gonna make it. Let's see, how many more slides do I have? Whew, okay, we're gonna have to go fast. Not quite as fast as that one time. That was silly. Okay, advanced file forensics format. Here's this name again, Simpson L. Garfinkel. He's a good buddy of mine. He like emailed me out of the blue. He's like, hey, can I get your dissertation? I want to use it to teach a class. I was like, yes, I made it. Simpson Garfinkel asked me for my dissertation. It was awesome. Okay, YouTube. Yeah, I'm sorry, dude. Never mind. Okay. Some of the design goals of this was to provide compressed format, no size restrictions, be able to have space in there for segmented files, for metadata. It's really simple, open source, internal consistency checks. AFD is, sorry, I just made the connection with work. AFD for segmented files, et cetera, et cetera. This actually has become more the industry standard, close to it. EO1 expert witness is still pretty standard, industry standard, but this is like number 2. Okay. My battery day. Oh, here we go. Okay, acquisition tools. So here's some of the tools that we can use to do acquisition. First is acquisition in Linux, preparing a target for drive for acquisition in Linux. A lot of Linux distribution could create partition tables for Microsoft file systems. Fdisk lists and creates partitions, and makefs.ms-dos creates file system. Acquiring data with DD in Linux. Okay, who's ever used DD before? Also known as disk destroyer, right? So the textbook calls it data dump, but officially there's no like, but the acronym doesn't stand for anything. It's just DD. That's the name, but I have to put it in quotes. We can read and write from media device files, creates raw format file. I'm hoping to give you a lab that will actually have you practice DD, but I'm still having trouble getting a hold of the laptop, so I apologize for that. Okay, here's some examples of using DD. So DD, IF, that means the input file. Here you put the source and then the output file for the destination. Then you get the block size. That's gonna make a lot more sense when we talk about disks and stuff in the next topic. And then you just do that, and then it'll tell you how many records or blocks it read in and how many it wrote out. Very simple, right? So let's say we have this file. We just want to copy a file. This is like the dumbest way to copy a file ever, because you could totally mess up your whole system if you didn't know what you were doing. But we have this file, and we're going to write it out to the destination file and use a block size of 512. Here, what we're doing is this slash means root, where you're looking at a Linux device. HDA is a hard drive, the first hard drive that the system finds. And so we're going to take that as our input, and our output is going to be this file name. So writing to map hda.dd, block size of 2K, and then what are we going to do? We're going to take the MD5s up, some of it, concurrent with the acquisition. Pretty cool, right? All right. Similar dev. So the input is dev SDA, similar, and then we're going to pipe it through this program called split. Yeah, basically we're going to split it into blocks of 650 meg and write it out to image.sda. Okay. I still got a few minutes. We're good. Okay, acquisition with ProDiscover Basic. ProDiscover is just a proprietary tool. That's all that matters right now. So acquisition format, it'll be split into 650, creates image files with an EVE extension, log file, special inventory file. Okay. You can also do raw acquisition, very similar to DD, and saves only the image data and hash value. Okay. None of this matters until you actually try to use it. That's why I'm not going into depth. Acquisition with FTK Imager. FTK Imager you can get for free. FTK you cannot, but FTK Imager you can. Included on FTK makes disk to image copies of evidence drives. Logical partition level, segment the file. Must have hardware right. Okay, so it does not do the write blocking for you, meaning you have to have something else protecting the original disk from having its contents changed. Okay. Write blockers, there's a whole bunch of hardware write blockers that you can have like in line between your tool and the actual evidence, but not a big deal. Okay. Or USB write protection, registry feature enabled, FTK image can't acquire drives host protected area. Don't worry too much about what that means. Just had to put it on there. Hey, we made it. Okay, so that's it for today's lecture. So yeah, next time we're going to talk about volumes and drives and files. Oh my, it's going to be awesome. So we'll see you next time.